Okay, so I'm actually, even though this is a 3 by 3 matrix, I'm actually on the second row, I'm only looking at the y and z variables. And I'm trying to find something that will be canceled out by those two variables. So I'm gonna swap these two and change the sign of one of them. Which one you choose to change the sign of actually doesn't matter. You can do either one. So I just chose to do it that way. Now that tells me what y and z are. Now let's go back to the top equation. The top equation is going to help me find x. So 2x plus 3 plus I times y, but I know what y is now. It's I. Plus 3 times z, which is 1 minus I, has to cancel out. So this is my equation, and I'm trying to figure out what x is. So I have 2x. Notice I have a 3i right here that's going to cancel minus 3i right here. Right? So what else do I have? I squared. What's I squared? Negative 1, right? I squared is negative 1, and I'm adding 3 to that. So negative 1, I add 3 to that, I get plus 2 equals 0. So what's x? Negative 1. X is negative 1. Very good. So I have negative 1 right here. Okay. Does this make sense? A little tricky. This is probably a harder than average example of where complex numbers might come up, because it's such a mess of a problem, but you actually had to do some EROs and play some games with it. But it's always good to practice on hard problems. You have a question?
Say we crossed off the wrong row, because like that matrix right there, it's hard for me at least to tell which is a multiple of one another. So what would happen if we crossed off the wrong row?
Actually, you could have crossed off any of these 3 rows, and it would have been okay. So none of those 3 rows are multiples of each other. None of them are. They are not multiples of each other at all. They are linearly dependent rows, however. They are, that doesn't mean they're multiples of each other, but they are linearly dependent on each other, because I know that when I massage out the linear dependency, I'm going to get a row of zeros here. I know that that has to happen. So these rows have to be LD. The only question is, can I just freely cross off whatever row that I want? Well, let me give you an example that's a little more obvious. Suppose that I had this matrix here. Right, and I'm sitting there, yeah, I know that these rows are linearly dependent, and I want to cross off a row. And let's suppose that I came in and I said, I'm going to cross off this row. Would that have been a good choice? No, because this row is actually not causing the linear dependency, right? It's the fact that these two are multiples of each other that is the problem. We should have been crossing off one of the rows that was involved in the linear dependency. In other words, what I'm left with after I've crossed off a row should be rows that are Li now, right? We're trying to cross off the linear dependencies and leave ourselves with linearly independent rows. Now, how many rows do I have in total? I have 3 rows total. So after I crossed off a row, I only have 2 rows left. I can tell whether 2 rows are Li or not. Are they multiples of each other? I can ask that question about 2 rows, right? Well, I can clearly see here I made a mistake, because after I crossed off a row, the 2 rows that I have left, they are multiples of each other, which means I still have my dependency in there, which I was trying to get rid of. Over here, it actually doesn't matter which row you cross off, because the 2 rows that you don't cross off will not be multiples of each other. I mean, does everybody agree that I cannot take, say, this row, the second row, and multiply it by a constant and get the 3rd row? You can clearly see that, because the constant, to make negative 4 into positive 4, I would have to use a negative 1, but negative 1 times these 2 entries doesn't give me these 2 entries. So I know that I've done my job correctly, because if I cross off this row, I'm left with 2 rows that are Li. That would be as if over here, if I had correctly crossed off one of the first 2 rows. And then the 2 rows that I'm left with are Li. Okay? it turns out I didn't have to cross off the first row, because suppose I crossed off the second row. If I crossed off the second row, it's pretty much equally obvious, I think, that the first row and third row are not multiples of each other either. And if I cross off the third row, the first two rows are not multiples of each other either. So there's no linear dependencies left after you cross off any one of the rows. Okay, does that answer your question?
Yeah.
Okay, good. Okay, so this is the vector that we came up with. Now let's try to write down the portion of the solution that corresponds to that vector. So does everybody remember? Basically, you have to write down e to the lambda t times v. So don't lose track of the process here. We have e to the lambda was 1 plus 2I times t, and then my vector is this vector right here, negative 1I and 1 minus I. Okay? And what you want to do at this point is expand these expressions out so that the real and imaginary parts are kind of separated. So for example, you have e to the t, right? E to the 1 times t, that's just e to the t. E to the 2it, how can we rewrite that?
Cosine of 2t cosine.
This is where the sines and cosines start to come in, right? Cosine of 2t plus I times sine of 2t. And then, so I've expanded out the scalar part. What do I want to do with this vector part? Exactly, bust it out so that the I part is separated from the real part. So the part that doesn't have I in it, so basically it's going to look like this. It's going to be something plus I times something. That's going to be the structure of how it's going to look. Okay? And what I need to do is just figure out what to put in here. So what am I going to put for the real part of the vector?
1, 0, 1.
Negative 1, 0, 1. Good. Does everybody see that? Okay. What about the I part? What's going to be in the vector here? 0, 1, and negative 1. Beautiful. Okay. So that looks real good to me. Okay. And now is where we do that FOIL, but we do it as FOI. And we do the first and last together. And then we're going to do the outers and inners together. That way, we'll extract the real and imaginary parts of the solution. So I'm going to jump right to the solutions here. Kind of cut out one step. Okay. So to get the first solution, of course, I have e to the t, which is out in front of everything, totally factored out. And then I'm going to take cosine of 2t times negative 1, 0, 1. There's no I in there, right? So cosine of 2t, negative 1, 0, and 1. It's going to look like that. Okay? So that's this part times this part. And then I'm going to do the last terms. So I did the first, now I'm going to do the last terms. And the last terms, notice I have I times I, which becomes what? Negative 1, and it'll be multiplied by sine and 0, 1, negative 1. So it's going to be minus sine of 2t times 0, 1, negative 1. Okay, everybody all right with that? By the way, if you want to, if you like how it looks better, you don't have to do this, but you can compress this solution and say, well, along the top line, I have minus cosine of 2t, and then I don't have any sine of 2t. And then the second line, I have minus sine of 2t. And on the third line, I have cosine of 2t, this is a double negative, so plus sine of 2t. Okay? You don't have to do that, but it is an alternative way of looking at it. Everybody comfortable with that expression? Okay. Now let's do the second solution here, which still has an e to the t in it. But now I'm going to do the outers and inners together, and I'm going to ignore the i's. Because remember, I'm trying to get an answer that doesn't have I in it. So what is it going to be? Can somebody help me?
I mean, sorry. I was already negative 1, 0, 1. Sine 2t negative 1, 0, 1.
Okay, so that's the inners. Sine of 2t times negative 1, 0, 1. All right.
And then plus cosine 2t 0, 1, negative 1.
Plus cosine of 2t times
0, 1, negative 1.
0, 1, negative 1. All right. I like that. That looks great. And again, I could choose to compress that. E to the t times negative sine of 2t, cosine of 2t, and sine of 2t minus cosine of 2t. Okay. Are we all right with that? This is 2/3 of the problem.
Where did I go on that second one?
We're dropping it.
Oh, just drop.
Yeah, it's like magic.
Okay, well, I got the magic on the first one.
Well, the first one doesn't have any I in it, right? Because the first one doesn't have I in it at all, because when you take this part times this part,
I see.
there's no I at all, right?
Okay.
And even on the last part, there's I here and I here, but I squared is negative 1, which is why there's a minus
Yeah,
there.
totally.
So you might be wondering why on the second solution I don't have an I out in front of the whole thing.
Yeah.
Because technically it is there, but here's what's going to happen. If you give me this grief about this right here, then this should be an I. I'm going to go back and say, you know what? I'm going to go take my other eigenvalue. I'm trying to save you guys work. If you take the other eigenvalue and you run through this whole nightmare again and do a whole other null space and blah, 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 right? You're going to get another solution that's got this kind of a form. And you're going to be able to take this solution together with the solution that goes with this lambda and combine them together in a way that cancels out the I. Basically, you can divide through by I anyway. I mean, think of it. I is, remember, this is a vector space of solutions, so it's closed under scalar multiplication. I can choose to multiply by the scalar 1 over I and cancel it. That's another way to think about it. Okay, so there's my second solution. All right, am I done with the problem? Oh, I don't know if I'll ever be done. We have another eigenvalue that we have to work with. What was the other eigenvalue?
Negative 1.
Negative 1. Okay, so let's check that one out. Should be easier, right? Shouldn't be any imaginary numbers on the other solution. Let's check this out. Lambda equals negative 1. So this time I have to do the null space of, and I've already lost my matrix, haven't I? I have to add 1 to the main diagonal of the matrix. So that should give me 0, negative 4, negative 2, and negative 4, negative 4, negative 6, and 4, 8, 8. Like that. Okay? Look all right to everybody? I'm going to do a little bit of ERO action on that. I'm going to take the bottom row and I'm going to put it on top and I'm going to divide through by 4 at the same time. So it's just going to become 1, 2, 2. Okay? And then the top row, I'll go ahead and put that one second. I'll just leave it the way it is. And the second row, I'm going to put that one on the bottom. Well, I guess I can just leave that one the way it is too. Okay, so we're just kind of reorganizing the terms. Everybody see what I did? Pretty simple. What would I maybe want to do next?
Add the first to the third.
Add the first one to the third one?
With
With a multiple of 4. Good. Okay, so take a multiple of 4 on the first one, exactly, and add it to the third one. And I get that, right? Yeah. Oh, I should have already known that I was going to get to cross off a row. So I can see that that row is a multiple of that row. So basically, here's what you have, more or less, right? Okay, so let's see. We're going to have z as a free variable again. Z is a free variable, and we call it t. If z is equal to t, can anybody figure out what y is going to be? Let's solve that for y. Whoops, this should be equal to 0. Sorry. So if I put in, so y is equal to, isn't it just 1/2 of, negative 1/2 of t, right? Yeah, negative 1/2 of t, all right. And then now I got to figure out x. Well, x plus 2y plus 2z has to add up to 0. So if I put in negative 1/2 t for y and t for z, I'm going to get, what am I going to get there? X minus t plus 2t is equal to 0. And so x is therefore equal to negative t. Good, all right. And what am I going to do now to get my vector out of that? Yeah, just kill the t from everything, right? See, we're reviewing for the final exam too. This is like old stuff. So just take out the t, get negative 1, negative 1/2, and 1. So what will be my third solution? If I want to write down x3, well, how's that one going to look? E to the negative t times the vector we just wrote down, exactly, which is negative 1, negative 1/2, and 1. The problem said find the general solution. So what's that going to be? How am I going to get the general solution now? Anybody?
C1 times x1t.
Be sure to write down x of t equals, go ahead.
C1
Uh-huh.
times everything you have for x1t.
Okay, I'll just write x1.
There you go.
All right, plus?
Plus C2 x2
Uh-huh.
plus C3 x3.
That's it. Okay. Very nice.
On the test, could we write that, but like write C above?
Yeah, as long as I can find your work, you can say, you can just refer to above. Yeah, that's totally fine. Okay, everybody all right with that problem? All right, I'm going to try and speed things up here a little bit because I'm taking too long on these. So let's go on to another example. Let me, maybe I'm doing the hard ones first, that would be possible. Yeah, let me do number 4, also number 4 on the sheet here. So let's solve x prime equals ax, where A is the matrix negative 2, negative 1, 4, 0, negative 1, 0, and negative 1, negative 3, 2. And I'm going to throw a little wrench into this on this problem and give you an initial condition, which is negative 2, 1, and 1. Okay? That is the problem we're going to solve. This time I'm not giving you any eigenvalues as hints. I'm going to make you figure them out. Okay. So let's see. What would you like me to do first? Cofactor expansion of this matrix? Right, you have to subtract the lambdas off of the main diagonal, and then what row or column are you going to expand this one on?
Second
Row 2, very good, okay, perfect. So I'm going to take the determinant of, let me just write down the matrix, I have to subtract lambda from the main diagonal. So negative 2 minus lambda, negative 1, and negative 4. I'm sorry, that's a positive 4. And then 0, negative 1 minus lambda, and 0. And negative 1, negative 3, and 2 minus lambda. And if we expand the middle row, I'll have negative 1 minus lambda times the 2 by 2 submatrix consisting of the outer 4 entries. Cross off that and that. So if I'm going to do that, I'm going to get negative 2 minus lambda times 2 minus lambda plus 4. Yeah.
Wouldn't you have to have a negative in front of the negative 1 minus lambda?
Plus and minus plus and minus.
Alright, so the plus minus pattern, the middle of the matrix is going to, actually all of the diagonal entries, always the diagonal entries are always plus. It just means you don't have to adjust anything. Okay? Do I want to multiply that all the way out? Would that be a good thing to do? No. If you do that, you're going to have a cubic equation you're going to have to find the roots of. You don't really want to do that. You're going to be better off leaving it as factored as possible, which means minus 1 minus lambda is already factored out. Leave it out there, right? Now the part in the brackets, that part, if you multiply out, then you'll be able to deal with it as a quadratic, and that's not so bad to deal with. So if I multiply out the part in the brackets, I'm going to get a lambda squared plus 2 lambda and minus 2 lambda cancels, and then I have minus 4 and plus 4 also cancels, just lambda squared. So what are my eigenvalues? 0, 0, and -1, right? You guys remember my little, I think I gave you a trick at one point. When you add up the lambdas, this is worth remembering actually, and I haven't talked about it a lot lately. When you add up all the lambdas, it has to be the sum of the diagonal of the matrix. So it has to add up to A11 plus A22 plus A33 and so on, depending on the size of the matrix. So if you do that here, with this matrix, you add up the main diagonal, you get -1. Well, sure enough, when you add up these lambdas, you get -1. And the other thing that is worth remembering is that when you multiply the lambdas, does anybody remember what the formula was for that?
The determinant?
It's the determinant of the matrix, exactly. So if you happen to know that this matrix has a determinant of 0, which is pretty easy to check by expanding the middle row, you have -4 plus 4, it adds up to 0. So this matrix has a determinant of 0. So that means that the product of the lambdas has to be 0, which it is. By the way, it means the matrix is not invertible. It's not, I think there's a group work about invertible versus diagonalizable. You know, they're not the same thing, right? You can have a matrix that's one without the other. So this is an example of a matrix that is not invertible because one of my lambdas is 0, right? Is it diagonalizable? Good, it's a maybe. We don't know yet. We don't know. We have a repeated eigenvalue, right? One of my lambdas came up twice, so now I actually have to check and see whether it pulls its weight or not. On the previous problem, we had 3 distinct lambdas, so we knew it was diagonalizable. On this problem, we actually have to think, we have to work it out. We have to work it out. Okay, so let's just check it out. So which eigenvalue would be the better one to start with? 0, the one that's possibly causing a problem, which is 0. So let's try lambda equals 0 first of all. So I have to do the null space of the matrix. Well, I just subtract 0 from the diagonal, so it just means I take the matrix itself. -2, -1, 4, and 0, -1, 0, and -1, -3, and 2. Do you see, guys, from the middle row that y has to be 0? And that equation in the middle tells you that y is 0. So in other words, 0 times x minus y plus 0 times z is 0. Based on that, y has to be 0. Once y is 0, you can kind of look at the first and third rows and ignore the middle column because the middle column is where y resides and y is 0. So if you ignore the middle column, do you see the linear dependency? You have -2 and 4, and you have -1 and 2. They are multiples of each other. So basically, so if we take this first row and we write it as -2x minus y plus 4z equals 0, and then we remember that y is 0 for a second, now you can see that z is free. I'll call it t. And as soon as z is equal to t, then what's x going to be equal? 2t. Exactly. so what is my eigenvector here? Yeah, after I bust out the t, I get 2, 0, and 1. And is this matrix diagonalizable or not? It's not. This eigenvalue did not pull its weight, right? Did not pull its weight. So, all right, let's think a little bit then about what we have to do. If that eigenvalue did not pull its weight, then, okay, so I can make one solution. I can make my first solution, remember how we make the solution, right? E to the lambda t times v. But in this case, lambda is 0, so the e to the lambda t part, that's just going to become 1. E to the 0 is 1. So it's e to the 0 times the vector, so it's generally just 2, 0, 1. It's just a constant. It's just a constant vector, 2, 0, 1. It's kind of funny. And now I need, okay, so if I want to solve this system, I have to come up with a second linearly independent solution. And we are in a situation where our matrix is defective. So this is now following up on the material we learned on Wednesday, kind of near the end. And again, remember, I have those videos that you should watch to really see a lot of the cases, but this is one of those cases. Basically, the form, when you have the problem of how do you come up with additional solutions, the form that you're looking for is this one. Okay? So we need to look for these W's now. This is the process we have to go through. Okay? Remember, of course, here in this case, lambda is 0, so it's really just going to be W1 plus t times W2. Let me remind you how this is going to look. We have this little diagram, which I kind of like to use, where we're going to start at the left. I had some people stopping by to ask about the homework yesterday, and they wanted to start with the middle here, the W2, and then go backwards. And you cannot go backwards because, the reason you cannot go backwards is because this matrix that hops from W1 to W2 is not invertible, so you can't undo it and go back to the left. So I want to choose W1 in such a way that it survives A minus lambda I, but does not survive the square of A minus lambda I. Okay? So that's the trick. Now, of course, in this case, the lambda is just 0, right? Lambda itself was just 0, so it's actually, I'm going to come back over here again. I'm trying not to use that far board because I don't think it's as easy to see it on the camera. So I need to find a vector that survives this matrix, but doesn't survive it twice. Okay, so let's see what that tells us. The original matrix A minus lambda I basically is -2, -1, 4, 0, -1, 0, and -1, -3, 2. And I need to square the matrix now. Does everybody understand why I'm doing this? This is really A minus lambda I squared. Just in this case, lambda is 0. So I have to actually square this thing out. So I multiply it by itself. So, hey, what the heck? You're reviewing matrix multiplication. How to do matrix multiplication here. So this is just going to be a little 2 by 2. Sorry, 3 by 3. I have to square it. Let me tell you what you get when you square it. Okay, I'm just going to do it quickly so we don't spend a lot of time on this. 0, -9, 0, 0, 1, 0, and 0, -2, 0. Okay. So that's what we end up with.